All right, let's get started. Hello, everyone. I'm Piero. I'm the founder of Studio Atelico, which is, this studio that we just started. And basically, what I'm going to tell you today is about a little bit of a tech demo that we've built that uses AI within a game. And basically, the purpose of that is to have characters that are dynamic, you can interact with each other, create emergent behavior. And fundamentally, the cool thing about it is that it runs on device, which is something that nobody else does. It's unprecedented, and it's really unique to the kind of things that we are doing. First of all, let me introduce a little bit about myself so that you have a little bit more context. With respect to many of you who are game developers, I've been doing game development just for the last year, really. My expertise is in AI. I've been doing it for like 15 years when it was not called AI, it was called machine learning. And did a bunch of things that are relatively interesting, worked at very large organizations, very small companies. I was at Stanford at some point during the postdoc, started my own company called Predibase, that is a company for doing fine-tuning of large language models and serving of them. Spent some time at Uber, where I was one of the founders of the Uber AI organization. We were doing all sorts of things from customer support to a dialogue system for Uber drivers, for the recommender system of Uber Eats. If you ever ordered anything from Uber Eats and you accepted a suggestion, hopefully it was good. If it was good, it's thanks to me. If it was bad, it was not my fault. Sorry, someone else after me actually probably changed the system because mine was great. But despite the fact that I've been working in the AI space for about 15 years, I have this long-lasting passion for games, like probably 99% of you. Started getting interested into computers thanks to video games. The first thing I ever programmed was a clone of Pac-Man on my Amiga 500, which is also dating myself, early 90s and things like that. Also, spent some time as a reviewer, editor, chief editor of EveryEye about 20 years ago, where I was basically running the Nintendo section of EveryEye. But basically, what I'm going to tell you today is not related with that, is related with the fact that AI is starting to impact gaming. I don't know if many of you have seen some of these examples that I'm mentioning here. On the left-hand side, this example of agents playing Minecraft. At the bottom, there's generative agents, which was a paper from Stanford that had pretty widespread of coverage, and I'm going to dive deeper into that. Then there's the ACE system from NVIDIA, a game called Suck Up. I don't know if you've seen it. It's like an interesting, fun game where you have to convince, you're a vampire, you have to convince people inside houses to let you in, because if they let you in, you can suck their blood, otherwise you cannot. And you have to convince them by basically chatting with them, right? These are just early games that are adopting this kind of technology. There's going to be much more of that in the future, most likely. But one of the bigger problems is the fact that adopting this technology today is, first of all, nobody has properly done it yet. So everybody's going to figure out how to do it. On the other hand, it's very, very expensive. I will show you some examples of that. And so that's some of the things that I'm trying to address. My interest started from this paper, actually. This was a paper from Stanford from late 2023 called Generative Agents, Interactive Simulacra of Human Behavior. And what they were showing was a simulation of a village. You can imagine it to be something similar to like Stardew Valley if you want, or actually probably closer to The Sims if you want. And there were 25 agents inside this simulated village, and they were interacting with each other. They were all entirely governed by LLMs. Their behavior, what they were saying, how they would interact with the world, everything was based on LLMs. The very interesting thing about it is that it was the first example of that, and it was really unstructured. So anything could happen in any cell of the board, really, that is this village. And the very interesting thing is that the behavior that the characters performed was very, very credible, was like human-like. And there were some examples of emergent behavior, which were the most interesting aspect of it. Without having to script anything, the authors managed to obtain some behavior that were like, again, unexpected. A good example here was this one where they just told one character that today it was their birthday. Each character also has memory, and so the mechanism there was to plug inside the memory of the character the fact that today it was their birthday. And they just saw what unfolded. What unfolded was that character met other characters during their day, started talking with them, and mentioned to them that it was their birthday and that they wanted to organize a party. And after that, these other characters chatted with other characters, and they mentioned the fact that the party was going on. And so basically, there was this spread of information across the village of this party happening. And funny enough, some of the characters actually went back to the original character, Isabella, and told her that they basically knew that there was this party going on. This was, again, completely unscripted. The only thing that happened here was basically generated by the mechanics of the game. The only thing that happened was that initial seed of telling the character that there was a party going on, right? Sorry, there was their birthday going on. And so when I saw this, I thought that that's extremely interesting. And for many types of video games, you can imagine all sorts of simulation games like The Sims is a good example, but also city builders, games like the Anno series, for instance. For all of these games, this kind of technology could be like very game changing. But I chatted with the author, June, and basically what he was telling me is that the way this thing actually worked is as a batch simulation. So basically they were moving one character at a time in a turn-based fashion. It was not real time. And that to simulate one day, it would take them more than one day to simulate, of wall clock time to simulate actual day in the game. And the most important piece is that it costed them about $1,000 of OpenAI credits per day of simulation, which obviously it's like at the very least 5 orders of magnitude too much for thinking about building a game with the same mechanism. And so that's actually the reason why I started working on this specific project to see if it was possible to, on one hand, make something like that, but that runs in real time. And on the other hand, making it so that you don't have to pay $1,000 to be able to play something like this. But actually, I wanted to make it run on device, so on the local machine where all the simulation was happening, because if that was true, fundamentally, it could be run for free. So that's what I set up to do. And this is like spoiler already, basically this is like the work from last year that I did. It's this, we called it GARP, for Generative Agents Real-Time Playground. And it's built using Godot for the basically game mechanics, the rendering and all these parts. But the behavior of each of the characters inside the simulation is all governed by LLMs that are running locally. The very nice thing about it is that we managed to run, I think, if I remember correctly, up to 30 different characters on a single GPU. In that case was a 3090, but now we also have it running on a 2080. And the next iteration basically runs on a M1 Mac. So like shrinking more and more and more the required hardware that is needed for being able to actually play something like this. And well, for the remaining of the presentation, what I'm going to do is to tell you a little bit more under the hood, how does it work? And if you wanted to build something similar, how you would go and do it. And also tell you a little bit about the tech that enables the fact that it can run on device, because that's not banal. Like it requires a lot of expertise to be able to build that. And that's basically what we are bringing to the table as a company. So let me start from the cognitive architecture. This is like very large strokes of how each agent actually functions and behaves. On the left-hand side, you have the perceive function. What happens is basically there is a ball, if you want, or like a circle, it's a 2D game. A circle that is drawn around the character, and whatever is inside the circle, it's something that the character can perceive. Whatever is outside the circle, it's something that the character cannot perceive. Once we basically subselect from the scene graph all the elements that are the ones that the characters can perceive, we interpret what these objects are. And it could be other characters, it could be objects that the characters can interact with, they can move, and they can like basically do anything with, right? Each single object has a bunch of affordances, which are what actions can characters do with them. And characters have affordances too. For instance, each character can decide to speak with another character, and in that case, a dialogue starts. After this perception step, everything that is perceived is put into like a long-term memory, so the character can remember everything that happened to them. The long-term memory is basically like a small database, if you want. We're using a vector database for that, for easy of retrieval. But one important thing about it is that basically each memory contains also a poignancy score, which is, again, obtained by using an LLM for obtaining the poignancy score. An example of that is if the character is a firefighter, for instance, if they see a fire, probably that's very poignant to them, and 10 days down the line, they will probably remember about that. But if they see like an empty chair, probably they will not remember about the empty chair. And so the poignancy score is a mechanism that allows us to basically filter and summarize the memories of characters. After the memories are put into long-term memory, there's a retrieval step. So the other memories that are relevant to what's happening to the character right now are retrieved from memory. For instance, if the characters are, let's say, eating an apple, they will remember all the apples that they have eaten before, where they hate them, or maybe if they bought some apples, they will remember about that. Equally important because it's a mechanism that allows for learning. If you don't retrieve the memories from what you've seen before, you have no mechanism, if you put something in memory, to actually be able to use it for real in a new interaction. And another better example could be if I speak with someone and then I meet them again, I want to remember what I told them last time, so that I can also tell them, like, call back to what I talked about last time. And so the memories that are retrieved then go into a working memory, which is a small set of memories that are currently used by the character to making some decisions. And basically the decision part is the act component, where the characters fundamentally, based on what they are seeing and what is their current goal, which we're going to talk about in a second, decide what to do in the world. And act, for instance, take an affordance from one of the objects and actually perform that. For instance, they decide to speak with someone, or they decided to eat the apple, or doing anything else that is available for them in the world. And that goes back to the perceive step, right? There's two other parts, the plan and the reflect part. Briefly on the reflect part, at the end of the day, or when a character has seen enough memories, what happens is that there's a filtering step, basically, where you look at all the memories that you've accumulated, you summarize them based on the poignancy that we were discussing before, and new memories are added to the long-term memory, and the old ones are evicted. This is a mechanism that helps summarizing. For instance, at the end of the day, I look at my memories, I remember just 2 or 3 more important things, and I write a summary of it, and I write it back into my memory, and I forget about all the empty chairs that I've seen during my day, for instance. The planning part, on the other hand, is something that happens at the beginning of the day, not at the end of the day, and each character has some description, and this description is textual, like basically just English language, and based on that, at the beginning of the day, a character creates a set of actions that they want to take during the day, and at every moment, they check if there's like, they end an action and they need to decide a new one. They look at what their plan is, and depending on what is available to them, surrounding them, they decide what to do. A good example is at the beginning, at the beginning of the day, the character decides that maybe they wake up at 7 a.m. and at 8 a.m. they want to have a breakfast, right? And so they, when 8 a.m. arrives, they look around and also retrieve from memories all the occurrences of coffee that they've seen in the past, and they remember that there was like a coffee shop down the road, and so they decided the best thing to do is to go to the coffee shop down the road. Putting all these things together, it makes for the pretty complex behavior of each single independent character. But how are these things actually implemented? Each of them is a set of functions that use LLMs inside them, and they fundamentally there's more or less 40 of them for this specific game. You can imagine that for other games, there could be like a different set of them. But for this game, there's more or less 40 different ones. I will not go through all of them, obviously, because there's a little bit too many, but I want to give you an example of one of them, which is the planning one. What an LLM function does is basically takes some inputs, in our case, game objects, and returns some other game object that can be manipulated by the rest of the engine of the game. And for the example of the day planning, these functions are composed of two components. One component is a template. This template is a string of text, really, with some slots described by curly brackets. This is similar to Jinja templating, if you're familiar with like web development, for instance, or like with Python format functions, things like that. So we decide this, we write this beforehand. And in this case, fundamentally, it tells the LLM that given some sort of information about the characters, it needs to generate a plan. And the information is not provided at this stage. It's just the template. Then during the game, what actually happens is that the template is filled with the actual values that are coming from the current moment in the game. And so in this case, for instance, I'm trying to obtain a plan for a character that is called Ludwig, who's a musician, a chemist, and wakes up early, and so on and so on. And at the same time, I'm also filling the other part, which is the part that related to the recent important events, the working memory component that I was talking about before. That's what it's reflected there. Third part is that there's usually one or few shots, and what that means is examples of outputs from other cases, if you want, that are useful for the LLM to be able to produce something that is similar to that. Gives them an example to anchor to, even if the actual output that we're going to produce is not exactly like that, right? And in this case, there's like an example of a plan for another character in another moment. And it's just, again, a mechanism to provide context to the model. And then the last piece is a mechanism to specify what is the format that I want in output. In this case, both for like transforming game objects into strings that are then passed into the prompt, those are like serialized as JSON. And in this case, it's basically the format of the JSON that I want back so that I can parse it into a game object once more after I obtain it from the LLM. Many models actually have a mechanism so that you can also specify potentially like a grammar or like a regex if you want for the output. That's particularly valuable because it's not a given that the LLM is going to give you something that is grammatical and parsable. And so if you enforce it through these mechanisms, that's actually really powerful because you don't have to do multiple attempts at generating something that is well structured. And so this is one example of how one of the LLM functions work. You can imagine there's more or less, again, 42 of them in this specific game. And when you stack them all together, what can you achieve? So here I'm showing you the fact that we created more or less 30 different characters, and each of them has their own personality, their own background, and their own daily plan, which are all, again, strings of text that are used as inputs with these LLM functions to decide what to do. And based on that, they basically create the plans. This is an example of the plan of this character, and there's eat lunch, and then chemist experiment, then he plays piano, and then he cooks dinner, and so on and so on. This is, again, everything is generated on the fly, right? As a consequence, when I was talking about the act part, this is what actually the character sees. At the bottom, you see all the objects that are available to them, surrounding them in their perception field. And so the character, given the current plan and given what is available to them, makes a decision on what to do and also has a reasoning of why that is the case. When they encounter each other, if they decide to, they can start to talk to each other, right? And the communication is pretty natural. These two examples are actually pretty bad examples because one thing that we did to make plans work really well is to force them to speak using dates, precise dates and precise time, which is not like any human being would ever talk with someone else. I would say, Andrea, I will see you like tomorrow or like Friday. I wouldn't say like the exact date and the hour, right? That's like a little bit of a thing that we had to do to make sure that it was easily parsable, the dates that they will talk about, so that they can coordinate easily. But other than that, other than the dates, the dialogue that they entertain with each other is pretty natural and is grounded by their personality, their lived experiences, and everything that they do. As the player, again, this is a tech demo, not really a game, but as the player, there's three ways to interact with characters. One of them is to chat with them. And whatever they answer, again, is based on what is happening to them, what are their memories, what are the objects surrounding them. There's two more mechanisms. One is the inject memory, which is what I was talking about at the beginning, and what we use to try to replicate what in the paper was a party scene. We try to replicate that, so we have this mechanism where you can go in a character and add something into their memory. And also you can give them orders, basically, to take some specific actions. These are the mechanisms of interaction. And some of the things that are particularly interesting that we discovered is that this architecture is sufficient for actually obtaining some very interesting behavior, like in particular goal-directed learning. If you want, on our website, there's a 8-minute video that shows this in all full detail. But what I can summarize here is we go to one of these characters, Ludwig, this chemist and pianist, and we basically tell them that they dreamed something up, this new compound called frisium, right? And we see what happens. What happens is that the day after, in their plan, you can see that during the lab work, they actually figure out something. They discover what is the structure of frisium. And then when they have to cook dinner, this is like a new thing that they learned. And so they decide to use frisium to cook that dinner. This is actually very, very powerful because basically these characters are fully dynamic, that they learn and they can evolve through a potential playthrough, right? And this is like a small snapshot of the actual party. So we tried to replicate exactly the same behavior from the paper. And basically we told one character, today it's your birthday, and they go around and they meet other characters and they chat with them, inviting them to the party and not showing like all the invites, but just one of them where the character meets one of their friends and basically invites them to the party. And then at the time of the party, basically everybody shows up and there's these like balloons that have their photons dance. And so they go there and they start to dance in the house of the person who's organizing the party. So mission accomplished. We basically replicated what the paper was able to do, but we are doing it for free, running locally and in real time, while the paper was doing it in batch and paying a lot of money for that. This is an example of one additional thing that we do, that is domain adaptation. Who in the audience has seen the show Rick and Morty? Raise your hands. Okay, I would say about half of the people. It's curious, like the other half, I don't know where they were for the last 10 years. This is like Nerddom 101 by now, I guess, right? So in this case, we created this two. Oh, it actually works. I don't know, shut up. And there are like a few other scenes like that. The point that I wanted to make is that, okay, another one, just another one. Yeah, Morty is not super assertive, I would say, like in the show. And so okay. So the point that I wanted to try to make here is that we also have some mechanism that I'm going to talk about in a second, where you can basically create characters that make it so that giving a few examples of dialogue that represents their personality and their style of speaking, you can make it into like something that is relatively credible given the character. So if you've seen the show, you realize that this kind of dialogue kind of matches what the characters are about, right? And that's a mechanism for potential narrative designers to inject flavor into the game that otherwise is kind of made up on the fly, right? So just as a recap, the difference between the paper and our work is that, on one hand, that, work was a science experiment. This is like actual, like a video game running in an engine, really. So that's a big difference. The original paper was offline and in batch. This is happening in real time. It takes several hours, actually more than a day, to simulate a day. In our case, you can like speed up and basically decide how fast time passes. In all those demos that you've seen, time passes like 1 minute is an hour. So that's the mapping that we were doing. It queries OpenAI, the original paper. This work actually all runs locally. And it all works in free-form text in the case of the original paper. This work actually works with the game objects directly. And so that's much more powerful and integratable within game engines. And the cost is the difference, like $1,000 a day versus $0. And so this is basically the foundation on top of which, after I built this, basically what I'm trying to do now is I want to make it general so that other people can use it for their own games. This engine that I'm creating, I'm calling it like an AI engine for video games, in an analogy to like a physics engine for video games, in the sense that it's kind of like a pluggable thing that you can plug into your game engine to, in this case, manage the behavior of characters, but not only. And the kind of things that you can do like lifelike NPCs like that. It's very easy to integrate. We're trying to make it as easy as possible to integrate so that the primitives in the game engines are kind of mapped one-of-one. And then, the fact that it runs on device means zero latency, zero costs, zero downtime, because again, if you're using OpenAI for this, obviously if the OpenAI is down, the game is down as a consequence, right? So it solves a lot of problems all at once. And it's built using like basically a proprietary game-specific LLM that is small enough to run on device, but high quality enough to basically match the large models. But it's specific to games, and that's what makes it unique. And basically the way it works is that this is like research that I've done in my previous company. Fundamentally, if you use off-the-shelf LLM models that are available for doing something like this, it just doesn't work. And in that image, basically, the gray bars are all the performance of different types of models on 30 different tasks. And you can see that the tall gray bars are basically OpenAI models, and the small gray bars are all openly available models that are substantially smaller that could run on device. So the gray bar alone does not reach the level of quality that you may need to be able to run this. But there's also the orange bar that comes from a process called fine-tuning, where you basically collect some data, and on top of that data, you adapt the small models to do one specific task from that data. And then if you do that, then you add a lot of performance and you match the performance of OpenAI models on the specific task that you're trying to solve. And so in our case, how did that work? Basically, we run the game, we collected the data using like a large model like OpenAI. We collected the data and we fine-tuned these smaller models that are basically adapters. So they are small models that kind of change the behavior of a larger model. And by using these adapters, then in the end, that improved the on-device version of the model. And it's basically a positive self-reinforcing loop of improvement. And you can kickstart it by, using also handcrafted scripts. The example of Rick and Morty is a good example, but you can also kickstart it by using a large model like OpenAI models in the cloud, just the very beginning of the first data collection step, and then all the rest the version that runs on device doesn't need that at all. And in practice, then at runtime, the way it works is you have this green box, which is the larger model, and you have a bunch of adapters that you have trained for the different tasks. If you remember those 42 different LLM functions, they are now mapped into these adapters, which are small models. And what happens is, at any moment in time during the game makes a request, like, I want to do planning. And then what happens is that that specific adapter is loaded in memory. Consider that these adapters are very, very small, like in the orders of few megabytes. So that specific component is loaded in memory, and the prompt is given, and the model produces an output. The moment that something changes in the game, and now, for instance, I'm in a moment when I have to, the character needs to chat with another character, then I can load the specific adapter that I trained on a character, let's say the adapter for Rick, for instance. And what happens is that I take the input and I produce the output. And fundamentally, the mechanism is I can hot swap them on the fly as needed. And that's what makes a small model like the green one that can run on device match the level of quality of a larger model on the specific tasks that you have trained your small models on. And so this whole mechanism, we are, again, embedding it into this AI engine that has both some low-level primitives, like, for instance, running the game-specific LLMs and also all the memories and the database that manages the memory, but also has higher-level interfaces like the behavior of the characters directly. So you can, for instance, have a class that is NPC if you want, and if you have like your own NPC in your own game, you can just import that class and basically manage the behavior of your character through that. It embeds in game engines. Right now, it works really well already with Godot because we built the first demo with Godot. And soon enough, it's going to be working well. Unity is probably going to be the third one. Now we're working more on Unreal to make it work on Unreal. And then the nice thing is that you can build whatever you want on top of it. This specific tech demo, GARP, was built using both Godot and the AI engine. But you can imagine that there could be many different games that could be built using this technology. Here are just some ideas that we ourselves are toying around because now we're starting building our first game using this technology. You can imagine something that is like fits really well GARP. So for instance, some social simulation thing like The Sims or something similar. But you can also imagine any kind of game where you need to do some sort of interaction or textual or voice or interaction with characters to be able to actually play the game. A good example could be a detective game. Or, for instance, we're working with one potential customer that's a company that does strategy games, and they want to do diplomacy through this kind of system. So instead of imagine civilization, instead of like giving diamond to Gandhi so that he doesn't nuke you, what you actually do, you have to speak with him and try to convince him. And maybe you have spies, and the spies give you some additional information about who they are, their behavior. And so when you have a conversation with them, you can use that information properly in dialogue with them, right? So this could be both sprinkled on top existing game mechanics or also be the core of entirely new game mechanics. Yeah, so that's about all I had to say. And I was trying to make as much room as possible for Q&A. We have 14 minutes, so I think that it's quite a lot. Thank you for your attention. Here, there's the QR code. If you want to check out on the website, we have the full video of GARP that gives additional details on everything. Check it out, subscribe to the newsletter so that when we put out the first game that uses the technology, you will be notified. Thank you so much. What questions do you have? Andrea, I know you have questions. Please. Also, obviously, later, if you want to know more, also if you want to see some cool mini games that we're building with this technology, happy to show them.
First of all, thank you very much for your talk. That was super interesting. I think I'm going to go with how do you do replanning, and if replanning has any issue? Because historically, it's one of the issue with going with the planning itself. So
yeah, so that's a very good question. There's one thing that I need to specify first. The planning that happens here is slightly different concept than the planning of the traditional game AI technologies, right? That kind of planning is usually like a kind of a logical planning where the actions that you obtain as an output is a strict set of actions that the character will have to follow, and obviously, if those are not available, have to do replanning, right? In this case, the plan is just a list of strings, really, and so it's more, let's say, something that you tell to the next moment the LLM what they should remember that they have to do, more than an actual strict plan or exact list of actions that they have to take, right? So it's slightly different concept, first of all. Second, it is possible that there are some situations where, I don't know, for instance, the character decides to go and take a coffee, they get there, and then someone else who's taking the coffee. So they have to decide what they need to do, right? And so in those cases, there's, I wasn't showing it in the cognitive architecture for simplicity, but there's basically a little internal loop of planning again, only for that action. So it's like very limited to that scope of that action. And the outcomes there could be multiple different outcomes. One outcome could be just wait and try again in a few seconds, for instance, which is usually very effective because, again, in the case of taking coffee, you just wait and try to do the action again. And at this moment in time, there's no one taking coffee, so you can take the coffee, right? And this wait loop, we do it a set number of times, like 3 or 4 times. And then if it's unsuccessful, then we decide, let's just take another action. What was the second best action that we could have taken? And we take that instead, and we start to do that, right? It's not super complicated. It's very, very simple, but it's effective enough within the context of this game.
Thank you. Got another one, if
Please. We have time.
There we go. We're back.
Okay.
I can't lean too far over to one side, it seems. There we go. Try again. I'll
Okay.
test with lots of questions later, but in the meantime, 2 that I thought would be a benefit to the hall. So you've moved the model into running it locally on device, which is, of course, that and awesome. So how much money is it going to, money and time does it take you to retune that model? And also, how big is the model currently when you're running it on device? Like, how much video memory are you taking up with it?
Yeah. Good questions. So I don't know if everybody was able to hear the 2 questions. I would say, how much money and time does it take to train these small models, and how big it is, and how much memory and how much resources does it take, right? So let me answer the second part first. What we have right now is a set of models. The one that we're mostly focusing on is 1 billion parameters. But where we want to get is to have a set of models that could go from the 100 millions to the 7 or 8 billions. The reason is some of the tasks may require more or less intelligence, quote unquote, to be able to be solved. For instance, if I'm a character and I meet another character, if I have to decide if to chat with them or not, it's mostly based on the fact if I know them or not, and if we have something in common. You don't require a very smart model to be able to make the determination. On the other hand, when you're generating the dialogue in the style of someone, like the case of Rick and Morty, then you need something that is a little bit smarter to be able to do that properly. And so what we want to have at a certain moment in time is a slider, kind of like a slider for resolution, but a slider for how big the model is, as a consequence, how smart the base model is. And the slider may not be in the hands of the player, but maybe in the hands of the developer while they're developing the game, right? And obviously, specific tasks may require different models. So at a certain moment in time, we can have multiple of them loaded in memory at the same time. So that requires some use of memory, and in particular for discrete GPUs, that we are right now kind of on the verge of that. Like, we're going to use a few gigabytes of that RAM, which is problematic if you're doing a AAA game, obviously, then you want to use all the RAM possible to do the most beautiful graphics possible. But if you think about like a cozy game or like an indie game, most of the times they don't use all the resources that they have available in the machine anyway. And so for those games, I think it's good enough for those games right now, and it will be good enough for the larger games down the line. Also, the direction towards which the entire industry is going is, unify the memory. And so as a consequence, the specific constraint of memory may become less important down the line. Also, already is like that on mobile devices. It will be more like that also on PCs moving forward, so most likely. Regarding the first question, so fine-tuning the models, the cost and the time. The nice thing is that first of all, you only need to do it once. So even if it is, during development, you may want to redo it a few times, but it's not something you have to do constantly, right? So even if it's a cost that is like, let's say, in the thousands of dollars, it's still something that you pay once and then you don't have to do it anymore. The reality is that every training for each of these independent models, the 42 different ones, each of them costed us about $10. So it's basically nothing fundamentally, right? And the time that it requires, depending on how much data you use, it may take from few minutes to few hours, not much more than that.
I want to ask how to distribute a game that is built. I don't know. So the or
yeah. So again, the question is how the distribution of the game works if players need to download something like dependencies or something like that, or if it's just regular game. The nice thing is that fundamentally you ship with a large file, which is the model weights, and a few smaller files, which are all the fine-tuned models weights. And that's it. They are embedded within the application that you're shipping. And so there's basically the only thing that happens is that the application is going to be a little bit larger than usual because, the weights of the models to begin with, they are pretty large. So there's going to be like, I don't know, 1 or 2 gigabytes more than you would do otherwise. But in the economy of games that are 80 gigabytes, that's probably not a huge problem, I would say. And anyway, it's going to be something that over time becomes less and less an issue. This is, I would say, really cutting edge, right? This is something that nobody has been doing so far. We will optimize it over time more and more.
If you have a game like Gungeon, if you want to make an enemy capable of learning from the player how to defeat it, what type of IA you need to use? Something like what you show us, or maybe there is a better one?
That's a great question. And probably someone like Andrea would be probably a better person to answer that, but I can give you my perspective, right? It depends. So in the specific case of something like Gungeon, and you're thinking about like learning from the player actually fundamentally means looking at what the player is doing and trying to anticipate it to a certain extent, or like set up traps for their usual behavior or something like that. I would say probably there are other techniques that are better suited for doing that. This kind of technology is particularly well suited where you have some form of interaction and intuitive logic, where with intuitive logic I actually mean just logic in the form of natural language. So something that you can describe, right, in natural language. The behavior of the player shooting in a certain way or like dodging in a certain way, it's probably hard to describe in natural language. It's much easier to describe it in terms of actual actions within the game. And if you deal with actions within the game directly, I think and you have to directly respond to that as an AI, I think it's probably easier to do it with techniques that use those things directly, as opposed to mapping into like a language and then trying to do something with it.
Thank you.
Are there other questions? Right, if there are no other questions, thank you very much again. Enjoy the rest of the conference.